All right, so in this video, we're going to look at how to solve a three-variable problem by using row reducing. So this is our initial system. We have three equations and three variables. X plus y plus z is 2. X minus 2y minus 6y plus 3z equals 18. And 5x plus 2y plus 2z is equal to 13. And so what I've done is, to start with, I've converted my system into an augmented matrix. So we have our 1, 1, 1, 2 on the constant side, 1, minus 6, 3, 18, and then 5, 2, 2, and 13. Now remember that if you're missing any variables in one of the equations, then what you need to do is fill in the 0 for the coefficient so that the matrix is complete. Now, it's a good idea to keep track of the row operations as you go in order to make sure that, particularly if you find yourself having made a mistake, you can go back and figure out what you were trying to do in order to try to find out where your mistake was. So I'm going to write down the row operations as we go and then apply them. Now, the goal for row reducing is going to be to get a 1 in all the diagonal positions and then zeros underneath them. And then we can either continue with the reduced row echelon form, or we can back solve from that point. We'll probably do both in this example just so that we have the complete example. Now, let's start. We have the 1 already up here, so we're going to use the 1 to get rid of the 1 underneath it. So the row operation I'm going to apply is going to be row 1 essentially minus row 2 is equal to, we're going to put it back into row 2. And I'm going to save myself some typing. I'm going to copy my matrix. Now, the first time you try to do this, it may be useful to actually write out the rows and the operations elsewhere on the side, but I'm going to do this component by component. So row 1 minus row 2 is going to give me 1 minus 1 is 0. And then in the next thing, I'm going to get 1 minus a minus 6. That's going to give me 1 plus 6, which is a 7. 1 minus 3 is going to give me a minus 2. And then 2 minus 18 is going to give me a minus 16. Now I'm going to have to do the same kind of thing, but with the next row, I want to cancel out this 5. So now I'm going to say minus 5 row 1 plus row 3 is going to go back into row 3. Now let's think about what that means. So minus 5 times this plus this is going to give me 0. Minus 5 times 1 is minus 5 plus 2 is going to give me minus 3. Minus 5 times 1 plus 2 is going to give me another minus 3. Minus 5 times 2 is going to give me minus 10 plus 13 is going to give me 3. Now, once I have the 1 and 0, 0, everything underneath it, then I go on to the next column and I go down. So now I'm going to be looking at this 7. Now, one strategy that we can have is going to be to just simply divide by the 7. That's going to leave me with a lot of nasty fractions. And what I can see, again, because I'm a smart human and not a dull computer, is I can see that I'm going to have a lot easier time and not introduce any fractions if I use this third row instead. So what I'm going to do is I'm going to switch the order of row 2 and row 3. So row 2, and I'm going to swap that out with row 3. So this will become -3, -3, 3, and this bottom row will become 7, -2, and -16. Now, again, why is that helpful? Because now I can do my next row operation, 1/3 row 2 goes back into row 2, and in fact, -1/3 row 2. So I'm going to divide everything in row 2 by a -3, and that's going to get me a 1 and a 1 and a -1. So I got my 1 in this position without having introduced any fractions. So now I am going to do my next row operation, which is going to be to take row 2, in fact, -7 times row 2, and I'm going to add that to row 3, and then I'm going to put that back into row 3. So -7 times 1 plus 7 is going to give me a 0, and -7 times 1 plus -2 is going to give me a -9, and then -7 times -1 is going to give me a +7, added to -16 is going to give me another -9. -16 plus 7 is -9. Great. So I've got my pivot. I've got my 1 underneath it. Now I just need to deal with the third row. And so I'm going to divide everything by -9. So -1/9 row 3 is going to go back into row 3. And so we're going to copy our matrix. And that's going to become a 1, and that's going to become a 1. And so what I know from this point is that z is equal to 1. Now, what I can do is I can back solve. So if I look at my previous equation, I have y plus z is equal to -1. So if I plug in y plus 1 is equal to -1, then I can get y equals -2. And then my top equation is x plus y plus z is equal to 2. And so if I plug in the y and the z that I found, I can solve for x, and I end up with, that gives me -1 on x minus 1 equals 2. Add 1 to both sides, I get x is equal to 3. So then my solution is 3, -2, 1. Now I can do this by back solving, and this is fine. If I'm using technology, then I really actually don't want to stop here and do the math myself, because there's, people are prone to making mistakes. So instead, what I can continue doing in my calculator is go to reduced echelon form. Now, there are certain cases, particularly if you have a dependent system, where you must go to reduced echelon form in order to continue. You can't stop here. So we're going to continue solving it and verify that we do in fact get these same answers with using the reduced echelon form instead of just echelon form. Now, for reduced echelon form, once I have my pivots on the diagonal and zeros below it, I now want to do the same process, but now I want to eliminate everything above my pivots as well. So I'm going to start with row 3 here, and I'm going to get rid of these ones above it. So my row operation is going to be row 3 minus row 2 going back to row 2, and I'm going to do the same thing, actually, not quite. I want to do negative row 3 plus row 2 back to row 2, and negative row 3 plus row 1 back to row 1. It's all about the signs, and you want to make sure you're not flipping the signs of your pivots and things like that. So -1 added to 1 is going to give me a 0. And then -1 added to -1 is going to give me a -2. And then if I do the same thing in the top row, -1 plus 1 is going to give me a 0. And -1 plus 2 is going to give me a 1. And then I need just one more. I need to take this pivot to get rid of this one. So that's going to be negative row 2 plus row 1 going back to row 1. So -1 plus 1 is going to give me a 0. -2 is going to give me a 2 plus 1 is going to give me a 3. And so again, you can see in this final column, I have 3, -2, 1, which was my solutions, and my equations are x equals 3, y equals -2, z equals 1, which is exactly what I got before by back solving. So again, the idea here is if you're using technology, let the technology take you all the way. If you're not using technology, it may in fact be faster to stop and back solve. But if you're in a system where you have a dependent system and you need to find a parametric equation for your solution, well, then you're going to need to go to this reduced echelon form and not just stop and back solve, because then your equations will be too complicated. You need to get rid of all of the extraneous variables when the system is dependent in order to get a nice clean expression. And you don't want to do that extra algebra because you're not just plugging in points, you're plugging in relationships between other variables, and that's just not good. And we'll do a dependent example in another video.